this slideshow is how is the periodic table organized? And the sub-question is how can you use periodic patterns to make predictions about the placement of new elements? The word periodic means occurring or reoccurring at regular intervals. You've learned about periodic patterns before in math class. So it's like repeated patterns. Okay, and there are some repeated patterns on the periodic table, and you need to know what those are and be aware that we can use those patterns to figure out the properties of elements, ones that we know and ones that we have yet to discover. All right, give you a little history of the periodic table. The periodic table organizes all the elements in the world in a very scientific manner. So before the periodic table, we just had the elements listed on little cards or pieces of paper, and people would pull them all out and look at them and try and figure out which element would react with what other element, and it wasn't really a very efficient method, and it was quite time consuming. So around this time, chemistry was starting to become more important, and people were becoming more interested in it. So there was actually quite a few scientists that were working at organizing the elements. Now, this was during the 1800s, and technically the late 1800s. And Dmitry Mendeleev was a Russian chemist. He was born in Siberia, but actually worked in St. Petersburg. And he became famous not because of what it says here, that he identified patterns and predicted properties of undiscovered elements, because actually several other people did that. But what made him famous was that when he wrote his book, he said that some of the atomic weights of some of the elements were wrong, and that if people went back and redid the measurements, they would find that they actually had different atomic weights. So when they actually went back and did the measurements again, they found out that he was correct, and that was quite surprising, and that actually was the thing that made him famous and made his periodic table rise above all the other periodic tables. So let's take a look at his periodic table. It's right here. This was his first one, 1869. And so you can see right now it's turned on its side. So you have hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and sodium here. Okay, so it's just sideways. You can see there's some question marks here. This one, and there's actually 100 over here. So he was able to look at this and say, I can tell you the properties of these elements. We don't know what they are. We've never found them. But I can tell you when we do find them that these will be its properties. This is what it will look like. This will be its melting point, its boiling point. And right here he has approximately what the atomic weight or atomic mass will be. So in 1871, you can see here that he's revised his periodic table. So you can tell he did this for a long time. And see, now we have hydrogen here, and he's moved lithium down. So he's rotated his periodic table. You got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, and you can see here these are the groups or the families that he's starting to develop or to put together. And once again, now you can see he's got a lot more question marks in here. Okay, and so he was saying, oh, I can tell you what the properties of a lot of these elements are going to be once we discover them. And so this is what really put his name on the map. All right, so he based his the periodic table on atomic weight or atomic mass. Now, since then, in 1913, Henry Moseley modified the periodic table and based it on atomic number. So in my mind, I would ask, well, why didn't Mendeleev do that? I mean, that makes sense to have it by that now when you look at the information that we have. But the reason Mendeleev didn't do atomic number was because we knew about the nucleus. So in the late 1800s, we knew about a nucleus, and we could find the weight or the mass of the nucleus. But we didn't have the technology, and we had not discovered protons and neutrons yet. So between Mendeleev and Moseley, there was a period of time where they actually found out that the nucleus had protons and neutrons in it, and therefore we found just the number of protons, which is the atomic number, and so Henry Moseley was able to modify Mendeleev's periodic table. So this is what his looks like. I mean, it's not that different, But there's just a few more things that you'll see if you look closely. You'll find that some of the elements have switched positions, and so it kind of cleared up a few things that Mendeleev were like, these aren't quite right, but I don't really know like how else to fix that, and at some point there will be some changes and everything will fall into place, which it has. All right, so what is actually in this periodic table? So just to kind of review the element block, the element block contains information about the atomic structure. Okay, so each block usually typically contains things like the symbol right here. We usually have the atomic number. Okay, you can see that in both of these. And then the element name. Now I will say the element name is not always there. Particularly sometimes in chemistry you start losing the element name because you just start to know the elements and you don't need the name. And then the atomic mass. Now you see this one has the atomic mass and this one does not. Okay. Now, just to kind of review, remember the atomic number is always smaller than the atomic mass. Okay, because the atomic mass is made of protons and neutrons, so both of those, and the atomic number is just the protons. So there's going to be fewer protons than protons and neutrons. That will be a larger number. In addition to that, sometimes we have things like the state of matter written here. Sometimes the electron configuration. And remember, this bottom number here is the number of valence electrons. So those are some other, you'll see other things when you take chemistry, but those are a few. All right, so organization. I'm going to actually open all these up here. All right, there we go. All right, the periods are the 7 horizontal rows. So you can see here the horizontal rows go across. And I always think of it looking at the horizon when like the sun is setting. And so that goes this way. And we call them periods. There are actually 7 different periods. And the elements in each period have the same number of energy levels. And you're like, wait a minute, I thought that we didn't have energy levels. Well, remember, energy levels for an electron cloud model are just areas where the electrons would most likely be found. So if somebody was searching for you in school, where would you most likely be? Okay, and so smaller atoms have fewer places where the electrons can be, and the bigger atoms have more places where the electrons can be. This is like the difference between having a really small school, okay, with fewer classrooms to look in versus a big school with a lot more classrooms in it. The other thing which we've talked quite a bit about are the groups or families. There are 18 vertical columns, and so they're the groups or families, and we've kind of gone through and put you in your group or family to work on some things, at least most of you. And then the elements in a column have the same number of valence electrons. So remember, group 1 has 1, group 2 has 2, going forward like that. Just a side note, the valence electrons determines the chemical properties of an element. So the valence electrons are going to determine whether an element reacts with something and how much or how quickly it reacts. So we have some that are very violently and explosive, and we have some that, you know, kind of varies in the amount that they react. And there are a few elements that don't react at all. So just to kind of keep that in mind, okay? And that chemical ability to react is based on the valence electrons. Patterns in the columns. All right, as I mentioned, the elements in a column have the same number of valence electrons. So group 1 has 1 valence electron, group 2 has 2 valence electrons, group 13 has 3. And this goes through the whole periodic table. The one exception is helium. Helium is in group 18, so you say, oh, 18 valence electrons. Now, it only has 2 valence electrons. That's because it's a really tiny, tiny atom, and it only has 2 electrons, and so it will only have 2 valence electrons. It's put in that family because it acts like all the other elements in that family. So elements in a column have similar properties. So helium is in group 18 because it acts like a noble gas. And it says here, example, noble gases. That's group 18. They are all gases, okay? They all have low densities. If you're a gas, you have a low density because your particles are spread far apart. And they don't chemically react. So helium can exist by itself as an atom of helium, and so can all of the other elements in that family: argon, radon, for example. The alkali metals are group 1, okay, things like sodium and potassium, and they are highly explosive and have high densities, meaning that they're solids at room temperature. Okay, and there are other properties that these things have in common, but these are just a few examples. Once again, you notice this note at the bottom: the number of valence electrons determine the chemical properties of an element. Clearly, that's a significant and an important statement to remember. All right, so some other patterns that we've discussed before. Elements are arranged by properties. You have on the left-hand side, you have metals. On the right-hand side, you have nonmetals. And on the stair-step line, you have the metalloids. So this is an interesting thing to look at, because you can see how once you've organized these elements by atomic number, okay, and then we've lined them all up like this, there's such a fascinating pattern here with the metal, nonmetal, and metalloid. These are metalloids right here on that stair-step line, or that zigzag line. You need to know where that is. It cuts right here between boron and aluminum. Okay, and then notice once again hydrogen over here. Okay, it is a nonmetal. So we'll talk about that in a moment, but I just wanted to point that out. All right, families. So once again, we're talking about the vertical columns here. The groups are families. There's your group number up top if you're not sure which group we're talking about. All right, so here we go. Group 1 and 17. These are our most reactive families. And so once we look at these and we go inwards from here and inwards from group 1 down, the ones in the middle, like group 13, 14, and 15, they kind of vary in their reactivity. So it's kind of like a sandwich with the breads on the end. Those are very reactive, and then it changes as it gets into the middle of your sandwich. Group 18 is not reactive. These are noble gases, okay? They do not need to interact with other elements, and you'll find out more why. More later. The reason why has to do with this valence electrons. It has 8 valence electrons, okay? And you can see here that the valence electrons goes in order from 1 to 8. Group 1 has 1 valence electron, 2 has 2, as we said before. All right. Hydrogen is the last thing to talk about. Hydrogen here, located above group 1, okay? He's not a part of group 1, he's above group 1. And he's put there often because he has 1 valence electron. And hydrogen has his own unique set of properties and makes it different from any other element in that group and different than any other element in any group. So that's why we kind of call hydrogen the super cool loner element, because it acts very special and it acts differently than all the other elements. And it's not alone, because you'll find that hydrogen can combine, and often combines, with all different kinds of elements for different reasons. All right, so just to kind of keep that in. All right, I hope you learned a little bit about the periodic table today, and you can use this to do the work in class, and use this to study so you have an understanding of the patterns of the periodic table.